We now look at the first Primal-Dual approach to solve this problem. Remember, in the Primal-Dual approach, what we want to do is we want to take some dual solution that's valid and then increase it in every step. And at the same time, from this dual solution, we create some integral primal solution, and we keep on improving the dual one until we have a valid primal solution. And to prove something, we need the complementary slackness. So let me remind you again. In the complementary slackness, it tells us if we have a valid primal and dual solution, then it's optimal if and only if these two conditions hold. The primal complementary slackness tells us a variable in the primal is either 0, exactly 0, or the corresponding constraint in the dual is exactly fulfilled. And the dual complementary slackness tells us the other way around, a dual variable is exactly 0, or the corresponding primal constraint is exactly fulfilled. So what we want to do is we start with some valid solution for the dual. That's easy, we just don't pick anything, all the y's are 0. And then we have an invalid primal solution for this, and that is don't take any edge. And then we keep on increasing those y values, and from whatever we have in the dual, we pick some edges until we have a forest that connects all the terminal pairs. So, the complementary slackness tells us if for some edge there's some value in the primal, then the dual has to be exactly fulfilled in the optimum solution. So if there's some edge with value greater than 0, then in the dual we have, if we take all the cuts that contain this edge, then the sum of their mode sizes is exactly the cost of the edge. So the edge is completely covered by modes. So what we want to do is we want to increase those cuts until some edge is completely covered. And that's then the so-called critical edge. And then we want to pick this edge into our forest for the primal solution. And we only want to pick those that are completely covered. So we iteratively build a feasible integral primal solution by this. In the beginning, it's just an integral and unfeasible one, but if we keep doing this, at some point it will become feasible. How do we find a violated primal constraint? That is, if there's some set such that none of the edges that leaves the set is chosen. Well, there are exponentially many, so finding one would take a lot of time, but if there is one, then we can easily find one by just looking at connected components. If we just look at the connected component that contains the terminal Si, then we can easily check, does it also contain the terminal Ti? If yes, then it's fine, and then it's fine for all cuts between those. And if it doesn't, then it's not fine, and then we found one cut that is exactly what is inside the component and what is outside that is violated. So for every pair, we either quickly see all constraints are fine, or we find one that is violated. How do we iteratively improve the dual solution? Well, we can just look at this component where the primal constraint is violated and then keep increasing it. So we have one cut where the constraint of the primal doesn't hold, so we have to increase the variable that corresponds to it until the constraint holds. And we increase it as much as possible. So we increase it until some edge on the boundary of it becomes critical. So some edge now is completely filled with modes. We cannot increase this component anymore. And then this edge we pick for our primal solution. Let's have a look at the algorithm. We have in the beginning our y is 0 and our forest is nothing. And then we check for all pairs of terminals if they are connected in the graph that's spanned by the edges in F. And clearly in the beginning they are not connected because we don't have any edge, so we just pick any component in this graph that contains only one of a pair of terminals. So for this component, the constraint doesn't hold. And then we increase the dual variable until for some edge on the boundary of this component, the constraint is exactly fulfilled. So this edge is full, or it is critical. And then we add this edge to our forest and we repeat. So in every step we find some primal constraint that's not fulfilled. We increase the corresponding dual variable as far as possible and then pick one edge such that the primal constraint becomes fulfilled. So in every step we make at least one primal constraint fulfilled. So what's the running time? Well, if we make one primal constraint satisfied in every step, then we need at most as many steps as we have constraints. But we have exponential number of constraints, so that would mean that we have an exponential running time. However, in every step we add an edge. How many edges do we have? There's only a polynomial number of edges in the graph. There's only a quadratic number. So it stops at the latest if we have added all the edges to f. That means we have at most n squared iterations here. And this check if there is some component that we can do in time corresponding to the number of terminal pairs. Everything inside here we can also do in time dependent on the number of edges on the boundary of this component. So this whole thing runs in polynomial time. The only problem we have is that we have all these variables for all these cuts, and there are exponentially many of those. But we can get around this by handling all those cuts where ys is 0 implicitly. So we don't even store a variable for those cuts. We only create the variables as soon as we need them. And then we only consider a polynomial number of those, and then it's also fine. But how good is this algorithm? Well, if we look at the cost of the solution we get from the forest, that's just the sum of the cost of all the edges in the forest. From the complementary slackness, we can relate it to the dual constraints, because we picked only those edges where the dual constraint holds exactly. So we have only picked those edges where the cost of the edge is exactly the sum of the size of all those modes that go over the edge. And if we want to sum up all these, then we can just sum up all the sets, look at how many edges are on the boundary and also in the solution, and multiply it with the mode size. That is because this ys for some cut s is counted if and only if some edges in the boundary of the cut and also in the forest. So it's counted exactly that many times. So this is just a shorter way of writing this. So we get some solution that has cost this, and the value of the dual objective function is just the sum over all ys. So what we get is some primal solution has this value. This is the value of the dual solution, so we know that the optimum is somewhere in between. So our approximation factor is just the difference between those, or the ratio between those, so it's exactly this. The problem is that this can be large. So there are examples where for every cut we have in the solution, the number of edges of the forest in the boundary is k. For example, this one here. We have pairs of terminals. All the S terminals are the same vertex. All the T terminals are different vertices. We have a complete graph. Let's say the costs are all 1. And then it could be that we have some mode around just this vertex. And this picks everything. So we have a dual solution with value 1. We have a primal solution with value k. So this only gives us a k approximation following from this. But the thing is, the solution we get, the forest here, this is exactly our connected components. So every connected component is a tree. And in a tree, the average degree is 2, or it's slightly below 2. So we have here the mode around a vertex that has degree k, and this is bad. if we had modes around all these terminals, and they all have degree 1, then there's exactly one edge of the forest around it, and then we get a dual solution that's much larger. That's probably k over 2, because we can have a mode of size 1/2 around all of those. And then we get something much better. And the problem here was that we picked a bad mode in the beginning that we increased as much as possible until we had everything. If we take the mode around each of these and we increase them at the same time until they hit each other, basically, until all the edges are covered, then we get something much better. And that's what we want to do in the next part, to have a primal dual with simultaneous increasing.